First of all, I want to great thanks to organizer, because in this hard time of coronavirus to organize conference, it's not easy. And this every year conference of Polynomial Computer Algebra is very great events. And so my talk has title Algebraic classification of matrix algorithm, and the main purpose of my talk is starting of investigation of the big matrix. Our area is area of big data, this area of supercomputer algebra. Not we have area of pure computer algebra, and now is area of supercomputer algebra. And we have not ordinary matrix, but a very big matrix. And what has happened in this new day and new era, I try to give my vision in this situation. The outline of my talk is first will be problems of extreme scale computing. This is my main purpose of my talk. Then a classification, the main example, because each theory started from some example, and the point 2 will be some special example, holistic decomposition. The third part is classes of matrix algorithm, and the last part is the examples of this algorithm in each classes. Okay. In abstract, I presented 4 main points of my talk. The first point is the purpose, because now we have time for widespread of use of supercomputer, and we are interested to have a very large matrix, and so we are interested in special algorithm for this very large matrices. Second point is that I believe that now symbolic algorithms are becoming popular, indeed in this time. The third, the new classification of matrix algorithm is the 3 classes. I exactly will speak about this. And the fourth point is this special role of recursive matrix algorithm. It's absolutely not the elementary understanding in this field, a very big gap, I think, and the specialists have no so strong attention to the recursive algorithm. It's a very important class for the supercomputer. Okay. Introduction is just three problems of supercomputing, but I cited here Jacques Dangar. Jacques Dangar is a well-known father of supercomputing. He many steps in our day in supercomputing was done by Jacques Dangar. This is his paper. This paper of it was 5 years ago. The conference was named the Mathematical Software, and the title of his talk was "With extreme scale computing, the rules have changed." And in this paper, he speaks about very many problems with extreme scale computing, and I like to put your attention to the 3 main problems. The first is the control the growth of the array of numbers during calculations. The second problem is uniform load of equipment, because it was not a problem for one processor, but if you have 10,000 or 100,000 of processors, how to uniform load this 100 processor is a very great problem. And the third problem is protection against possible physical failures of individual processors. The quantum effect make very if you have 10,000 of kernels, then you have a problem. You need to use it several hours to obtain solution of your task with very big probability. One of the kernel or one of the processor maybe became destroyed, and will be physical failure of one of the processor. And what has happened with your program when one processor destroyed? There exist many different strategy what you can do, but all the strategy is very expensive, because you must to copy your data each time, time to time, and very many very difficult special scheme to struggle with this problem. But I demonstrate that we can solve this problem in the way of using block recursive algorithm. This problem I try to explain how we can give our answer to solve this problem. And now the example, because let's see it for this example to understand the main problem. For example, I take a very popular algorithm that called Haletsky algorithm. No, my talk is about the O matrix algorithm. So if you ask what kind of algorithm we can consider, solving system of linear equations to make LO decomposition, LDO decomposition, to find kernel, and many others. But if you ask somebody what has happened with error, with errors which appear in your algorithm, then the specialist in numerical algebra say, you must do exchange rows and columns. You must do to put the to the diagonal the greatest elements, and do very many other things special to obtain the less error. But here algorithm which took at input matrix that is you cannot change, because this matrix is positive defined. Each leader minor is positive, strong positive. This is symmetric matrix, and we know the algorithm how we can solve this problem. We need to obtain something like LU decomposition, but in this case, U must be transposed to L. This is a particular case of LU decomposition when the matrix is symmetric and positive defined, and we want to obtain triangular matrix L such that product of L to the L transpose will be equal the initial matrix A. So this algorithm, you have no possibility to make change rows or columns. You cannot put the biggest elements to the middle and so on. So you must do just straightforward algorithm. Here it is some of the examples of this algorithm. A bit later I demonstrated more carefully. Now it's what is important. That important things, for example, 2 by 2. If you have matrix 2 by 2, this is the answer. The matrix L that we can obtain starting from the matrix A, that is symmetric matrix. We obtain the alpha, beta, and gamma, and we want to obtain the number ABC. A is square root from alpha. Then we can do division and multiplication and subtraction, and gamma is square root from thank you. Thank you. And gamma is the square root from D. So you can see here two operations of square root and several operations of multiplication, division, and subtraction. And now I demonstrate you experiments. What is experiments? We took several matrices. This is the order of the matrix. It was 4 by 4, 8 by n, and this is the square matrix that has the size 64. For each matrix, we took what is experiments. We take some matrix L. Matrix L is triangular. Each element is integer between 1 and 9. It's a little integer number. Then we compute transposition. Then we compute multiplication and obtain matrix A as initial matrix. We took this initial matrix, put to the Cholesky algorithm, and obtained the result. The result was some computed triangular matrix L. Then we can make the subtraction, obtain the calculation errors. For the matrix S, we can compute the infinity norm. That's nothing but the absolute value of each element, the biggest absolute value of the element of this matrix. We put here in this table. We do such experiments 100 times, and we put here the mean. The mean in this 100 experiments we put here. The maximal elements that appear in this 100 we put here. It's greater. This number is greater than this number because it is mean value. This is maximal value. In this first and second rows, you can see the standard double precision arithmetic, and this is a real result. What you can see here in this table, in the last column, this is a matrix of the size 64 by 64. And you can see that the mistake that we obtain, the middle mistake is about 8. The initial number was between 1 and 9. And the mistake was 8. And the maximum mistake was more than 100. Size was 64. And now my question. If you start to obtain the result for Cholesky algorithm for the matrix of the bigger size, what is the error you will see? How you can obtain any result with Cholesky algorithm? In the row number, in the other rows, we make the experiments with another matching. Here it is double precision, and here it is another precision. We have a possibility to make arithmetic operation when we took the matching word that has 100 decimal digits. If you have 100 decimal digits, then in the result, there is a logarithm of the mistake, of the error. For little matrix, the logarithm of the error is 10 in the power, no, Without logarithm, it will be 10 in the power minus 96. But logarithm, you can here, and you can see the very good result because it is very little computational error. And what you can see here, dynamic. Dynamic is normal. We can see here a good dynamic for if you take not 100 but 500 digitals, decimal digitals in one mentioned word. Then you can see such computational errors. You can see that if we have 500 in the input, the error is about 30 digits. You have no the same as like here. This is correct experiments. Everybody can do the same experiments because its equipment is very primitive. Classical algorithm of Haletsky. The matrix I describe here, this matrix, and everybody can do the same experiments and to see the same result. So for the question, where is the border between the big data and small data? In the problem of obtaining such like this LU decomposition, my answer, the border is near the number 64. Because the computational error became bigger than the elements of the initial matrix. In this table, we demonstrate what we can, if we take the order of the matrix bigger than 64, for example, 100 by 100 or 400 size, what we need to take the matching word to obtain the result that is, no, in the case when your initial data is integer, you want to obtain the error that will be less than 1. If it is less than 1, that's okay, because error is less than initial data, initial number. So we evaluate this number of digits, and we obtain that for, no, for example, if you want matrix 4000 by 4000, you must take the matching word more than 1000 decimal digits. It's a very big matching word. And this is a table for user. If you are a user of Haletsky algorithm and you think what you must do to take double precision, or you take another possibility. This possibility that we obtain from, for example, from Java matching language. We have a special class in Java that called big decimal. In this class, you can very easy to put the you needed number for the matching value in decimal digits, and then to start your computation. Before to starting the computation, you must put this number of matching value, and then to start computation, and then you guarantee that your result will be with some little errors. This is end of my example, and you must understand now that I see just two possibilities to struggle with computational errors. The first possibility is to obtain the exact solution if it is possible. The second possibility is to use to increase the number of bits in the matching word, or a number of digits in the matching word. I don't know another possibility. If you know, it will be good, but I see just these two possibilities. And so we must to understand in what matrix algorithm we can use the first, and for what matrix algorithm we can use the second, and maybe something else. I suggest to use these three classes of matrix algorithm. The first class is the irrational matrix algorithm. The second class is the irrational matrix algorithm when we use which may be expressed in radical. And the third class is the iterative, not straightforward, but iterative matrix algorithm not expressed in radical. This classification connection with the idea to construct the algorithm for big data. In first class, very famous algorithm like solving system of linear equations, calculation of inverse matrix and determinant, similar t-diagonal matrix you can obtain, and characteristic polynomial coefficient of generalized inverse matrix, kernel of the linear operator, LU, and LDU decomposition, Blue-Hat decomposition. All this algorithm is rational, and it's put in the first class. In second class, we know we can put here the QR decomposition and the orthogonal calculation of the similar 2 and 3 diagonal matrices, and maybe some another algorithm. For example, Haletsky algorithm. I forget put here. Haletsky algorithm is indeed in the second class. And the third class contains SVD decomposition, contains the computation of the eigenvalue matrix and the eigenvalue vectors and eigenvalue numbers, maybe something else. This is we have absolutely the same situation that it was in the solution of one algebraic equation. First class is solving just linear equation. The second class the same as equation of the second, third, and fourth degrees, and the third class is analogs of the iterative algorithm for solving algebraic equations that is have order higher than 5. Absolutely analog. All this was about the problem number 1 of the errors. The second problem is uniform load of equipment. And what we want, if you have very many cores, you must put a big part of the your algorithm and put it to some another cores. We say many researchers group try to obtain such spatial mechanism to extracting large independent subtasks. This is mainstream. You must have some possibility to take a big subtask from your big task and put it to another place. No, it is, you can see spatial runtime system, OpenMP, Star PU, Legion, PowerSec, this company from Jack Dangara, and OSR, HPX, SuperGlue, Quark, maybe other. And on the base of recursive algorithm, we make our system. Its runtime. Its title is DOP Amine Pine, DAP. This is made specially for block recursive algorithm. The third problem is problem of protection against possible physical failures of individual processors. And I now I demonstrate how we can struggle if you use a block recursive algorithm. Because the tree that obtain during the computation, you starting from the roots, and step by step you obtain such tree. And if in some moment the process number 1 send a big sum task to the process number 2 and wait the result, but he could not obtain the result, but the system told him that it's failure. The node number 2 have failure, and process number 1 could not obtain the good result. What has happened later? The subtask that was taken from this and put into the second computer will be sent to another places, because this tree grows absolutely a dynamic scheme, and this subtask will be sent to another places, obtain another subtrees, solve the same problem as it was for here, getting result back, and all this another part of the computation still as it was before, without any changes. So it is very easy to struggle against the problem number 3. But for doing this, we must have block recursive algorithm. And now I present examples, because you can ask me, you so many says about block recursive algorithm, but we don't know any of such, maybe. So I presented several examples. What about I want to say block recursive algorithm? So how many time I have? 10? 5? Oh, first example is nothing but matrix multiplication. You must divide matrix to 4 pieces, and instead of the 1 matrix multiplication, we obtain 8 matrix multiplications and additions. Second very easy algorithm. If you want to obtain inverse matrix for triangular matrix, it's absolutely easy, because you must to inverse 2 submatrix which put it in these 2 places. Inverse matrix A, inverse matrix C, and then put here such product, and this is inverse matrix, triangular matrix A you obtain here. This is absolutely recursive algorithm, because later you must do the same with these 2 matrices and obtain a pure block recursive. This is holistic decomposition. This is proof of the correctness of this algorithm, together with demonstrated this block recursive algorithm. What we have? Initial matrix is A, divided in 4 pieces. This 2 matrix is transposed one to other, and we search for some matrix H that is low triangular. And how we can obtain these blocks? Very easy. You must say that we know the solution, make transposition, then multiply this transposition for the initial matrix H, and then we can equation. Each block here must be equal to each block here, and we obtain such algorithm. The first step is make Cholesky algorithm for the block A1 and obtain the result B and inverse for B. The second step, we must multiply A transposed and B in the power -1, obtain C. Then to compute A3 block minus CC transposed, obtain F, and make Cholesky composition for the block F. And this is the result, and nothing else. This is all the algorithm. This is an example of structured matrix inversion. It was known for the time when it was Strachan publicated his very famous paper about the Gaussian inversion is not optimal. In this paper, it was such algorithm. It proved that the complexity is the same, inversion and multiplication, but nobody uses algorithm because it is not stable if the first element in AY1 will be 0, that algorithm is stopped and cannot work. But this is recursive algorithm, so I demonstrated here. 1 minute. Okay, it's enough for me. And this is algorithm that called recursive algorithm for computing adjoint and kernel. This is my algorithm from certain years ago. It was published. Here it is absolutely block recursive, and all this computation may be done in integer matrix if you want, without division operation. And you have here four recursive call. One recursive call, second recursive call, the third recursive call, and in the another picture you can see the here it is the last. This is the result. We obtain the result of this computations, and here it is. First, second, third, and fourth. Yes, four recursive call, and all other operation is matrix multiplication, division by number, multiplication by number, subtraction, and nothing else. So you can very easy to make the graph of such algorithm and obtain it recursive. Maybe this is not so interesting because I have little time. What we can do with algorithm of the first class? We can obtain exact solution. In what form? First, you can obtain the integer solution if you want. If you don't want, you can put to the prime fields, obtain solution in prime fields, and then come back. You can use another technique of algebra to obtain with not so costly solution, but it is a way for supercomputing. For second class, we cannot obtain the exact solution, but we can use a very big matching word. The example of algorithm in what we can do this matching word big and bigger used. And for the third class of algorithm, we must do yes. For the third class of algorithm, we must do more additional studies. I will not speak about this algorithm. And this is conclusion. No, conclusion the same. Thank you for attention. My time is over. Maybe you ask.
Thank you very much. And for audience who join us through the video stream, YouTube video stream, and from Zoom, I'm very sorry for some technical problems with Zoom's streaming for this talk. We will try before next talk improve the situation with Zoom stream, but in any case, in video stream is everything okay and okay just now, and everybody who can't to see and to hear through the Zoom stream, you can change the way to join our presentations, our sessions through the YouTube stream. I hope that in YouTube everything is okay with sound and with picture. And just now, questions to Gennadi. No questions? Maybe my questions to you about the class of matrix algorithm which is implemented in your math partner system. Everything you will present it.
No. We have. Thank you for your question, because we have very many algorithms that we realized in math parse system, and I have no time to present this algorithm because it's. I can answer. We have algorithm for generalized inverse Morpin rows. We have algorithm for computing kernel, and this algorithm of computing kernel and inverse matrix, or the biggest inverse for the biggest subminors if needed to obtain the inverse matrix, to obtain the LU decomposition, LDU decomposition, LU decompositions, and maybe some.
Okay.
Some more, but this moment we have two lines. One line you can see in the internet, in the mathpar.com or mathpar.ukmaidua. This is pure internet line. Another line we developed for parallel computation. With my student, and another line, and for this, because it's for equipment for the supercomputer, and this line for normal server that we have. And if you took the result from the internet, you obtain just not parallel but sequential variant, but the same algorithm, but it's sequential variant because in one processor. Everybody, if you want to work with the code of the math partner, I give you the possibility to copy this code from Git and work in the kernel of the math partner.
Okay, thank you.
Can I ask a question? Do you have any classification for sparse matrices?
Скажи по-русски, я тут не слышу.
Классификация разреженных матриц.
Well known that the Breuer decomposition is a very good algorithm to sparse matrix, and all this recursive matrix algorithm is very nice to sparse matrix because it's moreover. I can explain why it is. If you have a standard algorithm, you try to put non-zero elements to the main diagonal, yes? And this algorithm is the best way. When your element non-zero will be put into the another diagonal, and this kernel will be zero, and obtain the zero up to the end. And there exist many investigations, not mine, but another mathematician, that it's have a good for sparse matrix. It's very good recursive algorithm is nice.
Okay, and I add my short commentary of this question and Gennadi's answer. I think that what about sparse matrices and algorithm with sparse matrices is strongly dependent on the way of sparsing. Because a lot of different matrices could be called sparse matrix, but Breuer matrix and not Breuer matrix, and some algorithms are very good for one kind of matrix and very bad for other. And I think that
not this. This is universal. It's good for sparse matrix and good for dense matrix.
I say about what kind of sparse matrix do you work. Thank you very much. I think that we have no time for more questions, and Just before the next speaker is Vladimir Yuri Blenkov, and he will present the talk, joint talk with Vladimir here. Yesterday talk also, and just now maybe we need three, not more than 5 minutes to improve our streaming.
Нам же с вас надо слушать.
I'm sorry that just now we have only good sound in YouTube stream, but no good sound